reinforced masonry infills. Now here comes another very important part of the dynamic analysis of the structure, that is mode shape. Mode shape of a oscillation is associated with the natural period of the building. So it is a deformed shape of the building when shaken at its natural period. So building can have as many as mode shape as the number of natural periods. So for a building there are infinite number of natural periods. So this is the most important line that user needs to understand. Below you can see the picture here that in the first picture it is oscillating at its first natural period, that is it is translationally along x-axis. In the second case it is showing the translation along y-axis, and in third case it is showing the torsional, that is it is showing the rotational mode. So this is the most ideal behavior of any type of structure. If in the case of poorly planned building, what happens is that sometimes this rotational mode comes in the first place and in the translational mode comes in the second place. So that is a very dangerous behavior which should always be avoided. The deformed shape of the building associated with oscillation at fundamental natural period is called the first mode shape. You should remember this line. Second thing, deformed shape associated with oscillations at second, third and other higher natural periods are called second mode shapes. Third mode shapes, fourth mode shape, fifth mode shape, sixth mode shape, and I repeat, building can have as any number of mode shapes. So there are basically three basic modes of oscillation: pure translation along x-axis, pure translation along y-axis, and pure rotation about z-axis. So this behavior we had studied here. Number one thing is pure translation along x-axis, second is pure translation along y-axis, and third is somewhat mode shapes can be confusing in the beginning. If you are reading about the mode shapes for the very first time, you should always remember that overall response of a building is sum of all the response of all of its modes. So if we sometimes assume that the building had 24 number of mode shapes, so the building combined behavior is the combination of all those 24 mode shapes. In regular buildings too, location and size of the structural element should be such that the torsional and mixed modes of oscillation do not participate much in the overall oscillatory motion of the building. And adding brace or introducing structural walls can increase the torsional stiffness of the building. Obviously if we add the brace, we decrease the torsion very much. So but although we can add braces in the RC, in the steel structures, and we can add structural walls in the RC structures just to increase the torsional stiffness of the building. So it is not only the translation stiffness that we have to take care of, it is also the torsional stiffness that we have to take care of. So three factors influencing mode shapes. Number one, effect of flexural stiffness of structural elements. So the overall lateral translational mode depends on the flexural stiffness of beams relative to that of adjoining columns. So the fundamental mode shape of the building changes from flexure to shear as the flexural stiffness increases relative to that of column. This is also very important. The topic does not ends on the first mode, second mode, third mode, translation, rotation mode. It also continues to the overall lateral translation mode. This is somewhat shear type deformation behavior. Here you can see that the columns are also showing a curve in addition to the beams. So in pure shear type deformation behavior, flexural stiffness of beam is large compared to that of adjoining column, and column deformation is predominantly double curvature bending within each story, leading to overall shear type deformation behavior of building. So in low rise and mid rise building that are designed as per the code, the relative stiffness of members lies in between the above two extreme cases. So this is basically a shear type deformation behavior, and this is the flexural deformation behavior. And in practical structures, it is always a mix among this and this. Second thing is, what is the effect of axial stiffness of vertical members? So mode shape also depend on the axial stiffness of vertical members in a building, that is the column sizes and structural wall sizes. Small axial stiffness causes significant axial compressive and tensile deformation in columns, leading to single or double curvature flexural deformations. What happens basically is that if we decrease the size of the columns too much, it may lead to single or double curvature flexural deformations. And additional axial deformation changes the fundamental mode shape from shear to flexural, particularly in tall buildings. So we should always provide robust column sizes or strong column sizes. And pure flexural response is not desirable because of large lateral sway, particularly at higher. Here you can see that this whole building is showing the pure flexural behavior. So pure flexural response is not desirable because of large lateral sway, particularly at higher floors. So here what basically happening is that here you can see that deformation of this point is coming from this point to this point, and here you can see that deformation of this point is coming from this point to only this point. So in flexural type behavior, the deformation is coming here, and in shear type behavior, deformation is coming here, while in mixed behavior it may come in between this. So pure flexural behavior is that is why not desirable at higher floors. So designers should always ensure that the axial areas are large for building columns and structural walls. Here you can see that this is a normalized mold shape, normalized building height, small axial stiffness. Here you can see that the behavior is pure flexural. Here you can see that the behavior is somewhat like this. So here this is the shear type behavior, and here this is the flexural type behavior. Third is the effect of degree of fixity at the member ends. When we provide fixity, what basically happens is that the behavior is somewhat flexural. Here you can see that the columns are pinned here on the supports, and here the columns are fixed here. So this curve may help to decrease the deformation at the top. So the first condition is when the structural design and detailing deliberately creates rotational flexibility at those locations. So here in the case, this is the case of pinned and this is the case of fixed. So what basically happens is that highly flexible soil make column bases as hinged and rocky layer below as good as fixed. So lack of rotational fixity at column bases, that is in the case of hinged columns, it increases the lateral sway in the lower story then in the higher story, and here you can see that the overall response is like of shear type. And on the other hand, full rotational fixity at column bases restricts the lateral sway at the first story and thus induces initial flexural behavior near the base. So the overall building is still of shear type due to flexural deformation of the beams. And the fourth is the effect of building height. So here you can see that 5-story building is behaving like this, 25-story building is behaving like this, and 40-story building is somewhat behaving like a curve. So in well-designed low height moment frame buildings, the fundamental translation mode of oscillation is of shear type. Building become laterally flexible as their height increases, so the natural period of the building increases with increase in height. However, the fundamental mode shape does not change significantly from shear to flexural. So flexural type behavior is exhibited only near the lower stories, and at higher floor levels, the response changes to shear type as the axial load level also lowers. After that, we will study about the effect of mesh.